All right, hello everyone. We are ready to start the second session. My name is Shayan Monajjami and I'm a PhD candidate at Washington University in St. Louis. I'm delighted to introduce our speakers for this session. So the first paper is titled Case Study Comparison of Computational Notebook Platforms for Interactive Visual Analytics. Please join me in welcoming Han Liu for this presentation.
Hello everyone, good morning. My name is Han. Today I will introduce the case study comparison of computational notebook platforms for interactive visual analytics. Data scientists are looking to use visual analytics tools in making sense of their data. However, challenges exist when implementing visual analytics methods, especially for visual analytics notebooks, because the way of using notebooks is quite different between data science and visual analytics. It is also unclear what are the trade-offs in choosing between these platforms. So to investigate the problem, we use one example algorithm called Andromeda. And we also implemented Andromeda on 3 different notebook platforms. First one is a Python-based Jupyter notebook, and also JavaScript-based observable notebook, a Jupyter notebook embedded with JavaScript. Andromeda is a representative interactive visual analytics algorithm for high-dimensional data analysis. The reason why it is chosen is because Andromeda consists of both data science and visual analytics. It also contains interaction cycles and data iterations. Here's the user interface for the Jupyter Andromeda. It contains 3 main components: the sliders, which controls the weights for the high dimensions, and the scatter plot, which shows the 2D projection of the high dimensional data, and also the bar chart, which shows the inverse dimensionality reduction result. So all 3 components are created by Python in the Jupyter Andromeda. And for the observable Andromeda, it is also called O-Andromeda. All the code are implemented with JavaScript. For the Python plus JavaScript Andromeda, it is also called JEJ Andromeda. So we use the Python package called Notebook.js, so that the Notebook.js package allows us to embed JavaScript code into Jupyter Notebook environment, so that we can process data with Python and create visualizations with JavaScript. Here I'm going to introduce some major trade-offs just based on the comparisons. So the first one is coding difficulty. The coding difficulty trade-off is measured by counting the number of non-commented, non-blank lines of code, also called NCSL. So the differences of the result showing in the result are caused by the limitations of the platforms, not by the programmer's coding knowledge. For example, to perform MDS in Python, only 3 lines of code will be enough by taking advantage of the Python package scikit-learn. However, for JavaScript, we usually use a force-directed graph to achieve the same goal. Much more code is needed. The second type of trade-off is interactive performance. To compare the interactive performance for each notebook, we conduct a case study on a small animal dataset to measure the speed for specific methods. Here we only show one demo for the comparison of the dragging speed for the Python scatter plot and JavaScript scatter plot. So for the Python version, we can see there's a great latency when users drag the dot. And for the JavaScript one, we can also see the dot follows users' mouses quite tightly. And the third trade-off is notebook organization. For observable, notebook cells can be arranged in any order due to the reactive characteristics. However, in Jupyter, if a user wants to show the visualizations in the beginning of the notebook cells, they have non-trivial extra work is needed. Literally, they need to following 3 steps. So the first step is to create empty placeholders, then process data. And then they can fill in the processed data into the empty placeholders by running all the cells. The first trade-off is the button usage. For the J Andromeda and JJ Andromeda, due to the low speed performance of the graph rendering and some data science algorithms, buttons are used to divide the whole process into small chunks. It helps users to save time when they are waiting for the process to be completed. However, in observable Andromeda, since observable Andromeda usually have a cyclic system which contains non-deterministic algorithms such as VDS, which means once it starts, it will never end. So the buttons in the old Andromeda is used to stop the reference cycle. Please see the paper for more trade-offs, challenges, guidelines, and thanks for your time and patience. Any questions?
This was a fun talk, thank you. Leilani Battle, UW. One question I was wondering is, so you showed that the visualization implementation in observable was more challenging compared to Python, where Python you only needed 3 lines of code. One thing I'm wondering is part of the challenge we need to develop better libraries specifically for JavaScript, or do we need to build better integration between languages like Python and JavaScript? Like, should it be self-contained, or should it be more interoperable?
Yeah, so since it's sometimes, especially for some data science, when we implement some data science tools, it is not easy to find suitable JavaScript packages. But for Python, it has plenty of data science packages. But the trade-off is for Python, usually when we want to implement some interactive visualizations, the speed, it shows a great latency, and also sometimes it takes much more lines of code to implement. So I'm trying to make comparison and see, okay, what the 3 versions of Andromeda look like, and the pure Python one, the pure JavaScript one, and the Python plus JavaScript one. Yeah.
Great. Any other questions? All right, thank you again, Mark, for this great presentation.
Thank you.
This is yours.
All right, so our next speaker is Rebecca Fast, presenting her paper, Interactive Visualization for Data Science Script. Please join me in welcoming Rebecca.
All right, so as you said, I'm going to talk to you about interactive visualization for data science scripts. So as data science is becoming more ubiquitous across a wide range of domains, we're seeing some unique challenges emerge to how we debug and understand these analysis or scripts. And so one of these is that a lot of the tasks are more exploratory in nature, such as examining script behaviors under different parameter settings or different analysis algorithms. There's not really a right or wrong answer, but there are varying degrees of good and bad. And so it's important to be able to understand what makes one result better than another, and one way that we commonly would do this is to actually look at the evolution of those values rather than just the final result. Another challenge is the use of computational notebooks. So they facilitate a more iterative development process. And you also see this out of order execution of code cells where our common debugging practices don't really support this. And also these things like step-through debugging aren't widely supported in computational notebooks anyway. So to give you an example of the kind of tasks I'm talking about, let's say we have an analyst who is trying to balance cost versus production by using a gradient descent method, and they're trying to pick which one's the best one. And so instead of just looking at the final result, they want to look at how these values actually evolve and how it reaches that final solution. And so they start with a step-through debugger and they look at, cost versus production as they step through, but that quickly becomes cumbersome as they try to build a mental picture of what's happening, and they forget the earlier values, so they scrap that and go on to print statements. But again, you get this big dump of values, and you still have to try to serially inspect them and build this image in your head, even though you can recall a little bit better because I can look 3 lines up to see the previous value, right? It's still not really good for understanding what's happening. But consider instead, what if they were to use visualization? Let's say they had some fancy debugger that actually collected complete histories of these values and presented them like this, right? And so they can quickly get an idea of what's happening and how the values are evolving to reach their final solution. And they can see it has this weird oscillating behavior, and it reaches an okay solution, but maybe that's just luck, and maybe they need to try a different parameter setting or a different gradient descent method. But either way, it gives them a jumping off point for improving their analysis. But the problem is that traditional practices require a lot of manual overhead to actually produce these views and build these visualizations. So the question is then, how can we automatically collect and visualize execution histories to eliminate this manual overhead and support these data science debugging scenarios? And so that's where I'm going to present my tool Anteater, which is a trace-based visual debugging method. And so what Anteater does is it automatically traces computational notebooks and generates interactive visualizations in the notebook that then allow them to explore the structure of the execution as well as selected variable values. And so to give you an idea of how it works, we're going to walk through an example where this person was trying to implement a basic gradient descent in Python that was trying to minimize 2 variables, and it was returning not numbers, and they couldn't figure out why. And so I ported that over to a notebook and added the necessary function calls into the Anteater library, which is just an initialization call, a call to tell it what to track, and then once you've run everything, say, okay, now run Anteater and show me the visualizations. And so what it does in the back end is it actually goes in and finds the order which these cells were executed and rebuilds them into a program that it then instruments and traces. And the resulting trace is just a JSON file, which is fine for visualizing the execution structure, but not so good for visualizing the histories of the variable values. So we then port it over into a database, so we can use SQL queries to actually gather the data. And this is important because it makes Anteater a lot more extensible and flexible, because now any visualization we want to create, we just have to write the query to collect and organize the data. And so then it automatically determines what data or visualization to show based on what type of data it tracked. And so you get something that looks like this. Obviously, I cut off the bottom half, but you get a visualization of the execution structure, and then I'll show you more later, but visualizations of the actual values collected and controls to explore through the data. And so you pick which variable you want to look at and what type of plot you want to look at. And so since we want to look at the evolution of those values, we're going to look at a scatter plot. Right, and so from this scatter plot, right, we can see this value is supposed to be being minimized, but instead it seems to be all at 0, and then really low negative, and then infinity, and then a bunch of non-numbers. And so it's obviously not the intended behavior. And we suspect that those values aren't actually 0. So we think that maybe the linear scale is squishing them, so we can go ahead and change the scale to symmetric log. And we see that it's actually oscillating back and forth between positive and negative before it hits the infinity. And so what's happening is that the gradient is exploding, and we need to try a different parameter setting to improve the analysis. And so really the only parameter in this example is the training rate. So we go ahead and lower the training rate by a factor of 10, but it's still producing not numbers. So we don't even bother running Anteater because we know that's not the correct result. And so we reduce it again, and we get a number this time, but they're both really large, and so that makes us a little suspicious. And so we're going to go ahead and run Anteater to make sure that it actually is converging to a solution. And so one thing to note here is that when we run Anteater, because we didn't run it in between the 2 executions of that same cell, it actually was able to capture that out-of-order execution. Right, so on the left hand, we have that first call with the higher training rate where it didn't, was still reaching out numbers. On the right hand, we have the second call where it did reach a numeric solution. And so it was able to capture that behavior. But we don't really care about the left-hand side. So we can actually click into the execution plot to zoom in just on that second function call and just look at the values from that. And so then from the scatter plot, we can see that it actually is still oscillating. It's improved, it's not reaching odd numbers, but it isn't correct, right? It's not converging. So we go ahead and we reduce it again, and we see that these values actually look like they have converged, but just as a sanity check, we go ahead and run Anteater again, and now we can see that they have converged. Right, so using Anteater, we were able to quickly look at the evolution of these values and understand how our analysis was reaching them and whether it was a good or a bad result. And so it should be noted that we could technically do this with matplotlib and just instrumenting our source code, right? But the problem is that takes a lot more work. And so on the left, we have the 3 simple calls into Anteater. On the right, I instrumented it with matplotlib to actually gather that data, organize it, and then use matplotlib to plot it. And this takes a lot more effort. And if you're like me, who has to Google how to use matplotlib every time you use it, then this takes a lot more manual overhead. And the end result is quite different, right? With Anteater, we get several interactive visualizations. I didn't get to talk about the interactions between the two, but there are more than what I showed here. And you can also track multiple variables and quickly create plots of different variables. And so you get low manual overhead for multiple interactive visualizations, but with matplotlib and your instrumentation, you really just get this one static visualization for quite a bit more overhead. Okay. So to recap, Anteater automatically traces and visualizes data science script behaviors. And so it really does support these non-traditional debugging scenarios like we saw with these exploratory tasks where looking at the progression of values is more, provides more intuition than looking just specifically at, or insight, than looking specifically at the end result. And it was able to support these out-of-order executions of computational notebooks and collect those values and show them as well. And it also alleviates a lot of the manual burden of traditional methods, right? There's much less manual overhead. You just have to tell it where to start, what values to collect, and where to run. And so a couple things for future work. Rather than having it be a library where you have to actually make these function calls, we'd like to actually make it a Jupyter extension where you click a button, says turn it on, go through your workflow, and later say, okay, now I want to look at the visualizations. And so incorporate it directly into Jupyter. And last, we'd like to provide comparative views for inspecting multiple executions. So, for example, when you ran that same cell twice in a row, rather than having it plot all in one run of Anteater, have comparative views that plot the two in the same space to give you a direct means for comparing the results and evolutions through 2 executions. Okay, so that brings me to the end of my talk. I'm happy to take questions. Thank you.
Hi. So I have a few questions. So the first one is, can you keep track of variables like across different cells in the notebook? And when you change variables, do you have to keep logging them iteratively, or is it automatically taken care of? So
maybe repeat your question because I couldn't quite hear you. So you're asking if I can track them across cells by just defining them once up above? Yes, it should be able to do that. Yep.
That's awesome. And second question is, I see a couple parallels with like other debugging tools like TensorBoard or Sacred. So can you compare a little bit how this method is different and what are the improvements? Like I can see the notebook being a big improvement over the things. Do you have any others?
I'm sorry, I couldn't understand you.
Oh, sorry.
Can you pull your mask down maybe?
Oh, yeah, sorry. So I can see some parallels with other tools such as Sacred and TensorBoard. So I'm wondering if you have like some comparisons with these tools, like what makes the system like more powerful. So I can see like the notebook being one big contribution, but what other things make it better?
I'm really sorry, I'm struggling.
Oh.
I just couldn't quite hear what you were asking me to compare it to.
Oh, TensorBoard and Sacred.
TensorBoard, I see. I don't have much experience with TensorBoard, so I don't know that I can really comment on that one. So I'm sorry.
Hello. Okay, I'd like to ask about customization of this system or platform. So is it possible to put some custom visualization to interact with other predefined visualizations or?
Right, so we don't have it set up that way, but we designed the backend system so that you could very easily change the way that you do the visualization, right? We made it fairly modular so that you have the data collection side and then you could easily port it over to new visualizations. So while it doesn't do that right now, that is something that shouldn't be super complicated to add on in the future.
Okay, I actually have 2 questions. The first one is, so it looks like currently it's mostly tracking the values of the variables. Do you actually tracking other changes in the code? For example, you decided to use a different feature altogether. for the model?
I'm sorry, can you say that again? There's some idea.
Oh, so in terms of tracking the changes in the notebook, I think the example shows you change the values of, say, the hyperparameters, which affects the performance. Do you track other changes, which is not just a change of a value of a hyperparameter, maybe complete changing the code? For example, I decide to use a different classifier altogether.
Right, so yeah, so if you were to actually go back and completely change the code in a cell, it would capture that, because the way that it stores each cell as it, like the text from each cell as it is executed. And so it will track any changes that you make, not just like the changes from a parameter change, if that answered your question.
All right, so thank you again, Rebecca, for
Perfect, thanks.
All right, so next, I would like to introduce Maximilian Fischer, presenting his work on communication analysis through visual analytics, current practices, challenges, and new frontiers. Please join me in welcoming Maximilian.
Yeah, thank you. So my name is Max Fischer. I'm a senior PhD candidate at the Data Analysis Visualization Group at the University of Constance. And in this talk, we'll explore communication analysis and the role visual analytics can play in that. And in particular, we will look at conceptual framework for capturing communication analysis. Now, communication analysis occurs in several fields. It can be part of investigative journalism, for example, when studying large leaks like the Panama Papers. And traditionally, it's part of criminal investigations by the police or intelligence services. But it also can play a role in business environments when analyzing large collection of documents. What do I mean by communication data? Now, imagine you captured some telegram communication between maybe fighters in eastern Ukraine right now. And when you look at the data, you see several conversations of various intensities. The messages contain metadata like timestamps and the actual content, of course. And they talk there about particular topics. And further, you can also look at the conversational dynamics of the exchanges. The analysis of human communication then goes back a long time. Here we want to focus on the more recent core developments in the last century, from the 1900s onward. Now, significant research on communication was conducted in the area of psychology, and noteworthy there are the early works by Simmo on group formation and the human nature of communication by Cooley in the 1900s. In the 1920s and 30s, Lippmann published on the disparity of expression, and Moreno investigated interpersonal connections more closely. And then in the 1950s, VDS and Lewitt conducted their famous group communication experiments. The more modern communication analysis really started in the 1960s with computer-aided modeling by Shannon as well as Savannah and Deutsch. And communication analysis then took really off in the 1960s and 70s with the theory of media by McLuhan, the works of communication analysis by Watzlawick and Jackson, and interhuman communication by von Thun, as well as then the research on communication networks by Roger. Now, it's essential to note that all these approaches extensively consider and include the human factors in the communication context. When we look at the last 30 years in the advance of digital processing, there's something interesting which we can note. With digitalization, we really developed more of the analysis completeness, and this developed counter to the level of automation. So we achieve increasing specialization, but also isolation. And this is evident when we look at current approaches, because very few approaches really support an holistic view on communication analysis, which is in contrast to classical communication research. And this is the gap where visual analytics-based approaches can come in. Now, visual analytics can support and enable a more comprehensive analysis and reduce the manual work required, as well as address privacy concerns, which we have shown at the ACM Fact in Seoul earlier this year. It can also lead to a reduction in domain continuities and enable better support for the detection of cross-matches. These are findings that only occur when you consider everything in context. Now, it can also foster a more interdisciplinary approach, like in psychology and classical communication research, while enabling a more effective exploration that is less incomplete and less biased by analyzing the problem from a wider angle. The problem is that there's no categorization or taxonomy, and the role of visual analytics hasn't really been explored systematically in this field. And this is why we contribute a conceptual framework for communication analysis that describes and formalizes the existing state of the art and identifies ongoing challenges. And this framework is based on the existing research landscape, the existing works in communication research and psychology, and technical considerations. To achieve this in our work, we conducted an extensive survey on the properties of semi-automated communication analysis systems. We then reviewed the conceptual framework before using it to identify challenges and new frontiers in communication analysis. Let's have a look at the development process of the framework. We focus on approaches from high-quality VA journals and conferences in the last 15 years, searching for variations of the term communication analysis. We then went through manual filtering, manual coding, and finally manual validation, arriving at 41 approaches that partly that can be considered to work in this area. Further then, we conducted expert consultations with 8 domain experts about approaches used in practice, as well as the analytical needs and perceived challenges would influence the framework. After then multiple iterations, we arrived at a conceptual framework of communication analysis systems. And the framework here consists of 4 main dimensions, which is input, data and information, processing and models, 3rd, visual interface, and 4th, knowledge generation, which is inspired by the process model by Keynote. Now, each category contains several properties and sub-properties, which allow for systematic analysis of these systems. And note that these properties are also multifaceted, so for a detailed analysis, it's probably best when you look to our paper, because these are not really mutually exclusive in all the senses, so there are a lot of different options there. Now, in terms of the input, we distinguish between different properties of the messages, like data type, the codings of the message, the types of properties of the communication participants, as well as the context of the environment, like the medium or the confidentiality level. For processing and models, we consider analytical goals, like representation, exploration, and the scope, what type of modalities are included, the properties of particular methods, like what's the time delay, what's the scalability we heard about earlier today, latency issues, or data mappings. And for the visual interface, we consider representation, what kind of visualizations are used, the different interaction methods that are employed, and the different manipulation types, as well as the refinement particularities, like the goal or the strategy. For the knowledge generation, we evaluate the output regarding the explanation type of the learned model, the verification factors that are involved in this, the evaluations performed, as well as the analytical power of the knowledge gain. And when we analyze our approaches according to these aspects, we arrive at a complete survey you can see here. It contains 41 approaches analyzed according to over 50 different properties. And what we can note here is that we have a roughly equal footing regarding the primary visualization technique. So node link-based, timeline-based, or multi-paradigm visualizations are more or less equally represented, while there's a bit less focus on matrix-based visualizations and other more specialized approaches. The whole survey is also available as an interactive website at communication-analysis.dbvis.de, and it's further permanently archived at OSF. It wouldn't now make sense to really zoom in here, it's quite small, to discuss the complete table, so I want to highlight a few very interesting findings to you. These are 12 major areas of research where you can still improve on them, we think. So regarding the content analysis, the detailed analysis of the meaning and the analogical code, that means the hidden messages in between, is not really well supported in current approaches. Also, the context of the communication, as well as the participant relations, are often not included, probably because they're really hard to come by in a real setting. This includes power relations between the participants, for example, boss versus employee, and also the measurement problem, or you can call it adversarial attack resistance, when you know that your communication is basically watched or analyzed, and you might use keywords to communicate. Further, on a technical level, batch analysis and live analysis are not really supported, as well as progressive analysis. So in terms of processing, the merging of different data sets and groups is not widely supported, And in the visualization domain, the interactive analysis of a learned or trained model capturing the knowledge there is not really available. This also applies for knowledge generation and the model learning in general. Further, as we said before, trust and privacy implications, which are enormous in this kind of research, are really not that much explored, and there are no really guidelines on system development or quantitative user studies in this regard. Overall, holistic approaches are missing, and the combination of different contexts in the analysis is also not really well supported. Now, as a takeaway, we conclude that communication analysis has really transformed significantly within the last 30 years. It moved away from manual analysis to computer-aided and highly automated analysis, but by doing so, it has become less holistic and increasingly specialized and isolated. Now, in our work, we contribute an extensive survey and a conceptual framework for communication analysis, which leverage visual analytic techniques. And this framework allows us to assess the maturity of these approaches and the capability of existing ones. An additional expert evaluation with 2 domain experts confirmed that this framework is well structured, largely complete, and helpful, especially for capability evaluations. And we find that several challenges remain in communication analysis, offering wonderful research opportunities. For example, analysis of the analogical code, support for group communications, model building, trust and privacy considerations, the analysis of the context, as well as the development of holistic approaches. And thereby, our contribution has highlighted which is intended as a first draft of communication analysis and a stimulus for further considerations. And with that, I'm happy to take questions. Thank you.
To what extent do the methods that you've looked at handle missing information, like some, or combinations of information where information is available and information is missing, like some of the messages are encrypted and some of the messages are clear text. Sometimes you know who the recipient is supposed to be, sometimes you don't, stuff like that.
Yes, so this is really a big problem in many of the approaches, as you could have guessed. So this is very individual to the kinds of approaches we look at. Some support kind of just ignoring the messages. Other ones try to use some of the data that's available for these messages and then ignore the missing parts. But in general, really a combination of that is not supported in common approaches, I would say.
All right, thank you again.
Thank you.
All right, so once again, thank you to all of our awesome speakers. Now, I would like to hand this off to my awesome advisor, Professor Alvita Udley, who will introduce our keynote speaker. All right, Alvita.
Thanks, Sean, and thanks for all the speakers in the second session. I just realized that, I don't know if anyone knows this, but I did my PhD at Tufts University, so Remco is also my advisor. And he is actually a pretty humble person, so I'm really glad for the opportunity to make him feel uneasy. So I am honored and proud to introduce our second keynote speaker today, Dr. Remco Chang. He's an associate professor of computer science at Tufts University, and he single-handedly built a presence of visualization research at Tufts. He's the director of the Visual Analytics Lab. He has also spearheaded several research agendas throughout his career. So if you look at his bio, one of his best-cited papers defines insight and talks about using insight to evaluate visual analytic tools. He was also one of the pioneers in terms of looking at how personality influences analytic behavior. He was also one of the pioneers for visual analytics. He's currently working on visual analytics to explore high-dimensional data spaces and applications of material sciences to help scientists discover new materials. Because of his impactful research agenda, Remco has amassed millions of dollars in funding from agencies Such as the National Science Foundation, DARPA, the Walmart Foundation, just to name a few. He has advised students who have gone on to become rising stars in the visualization and HCI communities. In addition, Remco has won numerous awards, including, including the prestigious NSF Career Award, and his papers received best papers and honorable mentions at top venues such as ACM Chi, Euroviz, and IEEE Viz, and he has served as papers chair for visual analytics at the Viz conference, and is going to be one of the conference chairs for Viz 2024 when it's going to be held in Florida. On a personal note, Remco is also really hardworking and Remco is also really hardworking and a down-to-earth person. Even through his trail of successes, he strives to make the Viz research community more inviting, especially for junior faculty. So I'm delighted and honored to introduce my mentor and friend, Dr. Remco Chang.
Oh. Man. You know, you think you work with students, so they'll go off and do great things, except that they do things to embarrass you in front of a very large audience. So, but thank you so much for all those kind words. I'm not sure what to say right now, feeling a little, but thank you so much, everybody. I really do appreciate it. Okay, so, right, so today I wanted to share with you some work we've been doing for the past year or so. And the title of this talk is Towards a Unifying Theory of Data, Task, and Visualization with a Grammar of Hypothesis. Now, before I start, I know, the title of this talk is absurd, but I did say towards, so that makes it okay, right? So, and I need to acknowledge all the people who did the hard work. So Ashley Sue is a PhD student. This is her thesis topic. And she just gave this presentation, a better version of the talk I'm giving right now. She gave it the doctoral colloquium. Ab Mosca recently graduated, is in Northeastern, and Eugene Wu is a collaborator at Columbia. And the content of this talk is largely based on this archive paper. I'll share the link at the end as well. So here's my problem statement. Can you tone down the echo a little bit? Yeah, just, okay, does that help? Oh, okay, all right. So here's my problem statement. My problem statement is that visualization people are way too nice. So we get together, we have great conversations, we hang out, and we're really friendly to each other. But over the years, we now have a number of taxonomies on visualization tasks. So here's a list, a select list of the papers that I'm aware of that have touched on the question about task and visualization. So as a community, we're very friendly. We want to incorporate all the prior works of people that came before us. But as a result of this, our taxonomies keep growing and they rarely shrink. Right? So at this point, our definition of what is a task is getting to be a little complicated. So the word task and visualization can mean almost anything that a user wants to do with their data. So for instance, looking up a value. That task was first introduced by Roth and Mattis in 1990. Comparing two or more values, that's also in 1990. And then we have identifying clusters. So that's Warren and Lewis in 1990. Discovering outliers, so that's Amar, Egan, and Stasko in 2005. And more recently, Matt Bremer and Tamara Munzner added on top of these tasks to include presentation of results and joining and visualization. Altogether, these tasks now span data retrieval, statistics and machine learning, and now social interactions. Right? So now the diversity of these tasks make it increasingly harder to operationalize the concept. So obviously the question is, why do we want to operationalize the concept of task? And perhaps I'm just preaching to the choir, seeing how everybody here is interested in data viz. But we teach our students in Intro Viz course that choosing an appropriate visualization depends on both data and task. And without a formalization of task, currently what makes for a good visualization very much depends on the user. So this challenge was originally noted by Jack McKinley in his thesis, the APT work, which became Tableau and Show Me. But even though we've had decades of working on this, this challenge about how do we operationalize tasks remains open. So by and large, software systems like Tableau and Show Me still rely on data types to recommend visualizations. So in this talk, I'm going to be a bad guy, and I will do the inverse and try to reduce the definition of task. In particular, I'm going to say a task is kind of the superset to what we think of as analytic questions, which I'll define a little bit. And then lastly, this is going to be a superset of what we think about when we say hypothesis. And I'm putting the word scientific in here, and I'll explain a little bit why. But first, let me just kind of give an intuition about what I mean when I say analytic question. And I think what I mean by analytic question is very often referred to as analytic hypothesis in the visual analytics community. We use this term quite a bit, and we mean it in kind of a slightly loosey-goosey way. So for instance, here's a statement from the VAST Challenge 2017 where it says, provide a hypothesis of what the pattern of vehicle activities represents, right? So in this context, a hypothesis is not, it's almost like a mental model or some sort of understanding. We have a very similar thing from a recent paper where in the paper they talked about evaluating the following hypothesis. Would adding additional information about a geographical context improve the accuracy of building recognition? Again, here the word hypothesis is meant to be kind of a mental model or some sort of explanation in almost like human language kind of way. But compared to tasks, when we think about analytic questions, it's already kind of a step forward because they're more specific about finding some mental model or model to explain observations. So this makes the definition a little narrower, but for our purposes, it's still a little too vague to be operationalizable. So instead, we turn to this notion about scientific hypothesis. So we reduce analytics questions to hypotheses. And this is where you have to kind of remember your middle school, high school science classes, right? So remember when you're actually doing real science, you know, in a real lab. And your teacher probably told you about what is a good hypothesis, right? And it turns out that the properties of a good scientific hypothesis are quite clear. People have been studying these for decades. So we got this particular article from a science education venue where they talk about a good scientific hypothesis being testable and falsifiable, that is a relationship between at least two variables, and it has to be a quantified or qualified relation. And finally, it is something that you have a statement of how you would test this particular statement, right? So as an example, right, in a scientific hypothesis, you would say, well, you know, if I heat up this thing, so essentially if temperature goes up, volume will also go up. Right? All right, so so given such a clear definition, we can start to think about this in a formal way. So we're gonna go from this hypothesis definition into a more formal grammar. Now I caveat this by saying, I think of this as a conceptual grammar. It's not a grammar where you're gonna start implementing tomorrow, but it's more of a mechanism for us to think. So the first thing I have is that a hypothesis is defined as an expression followed by an operator, followed by an expression. So for instance, the average price greater than 10, or the average price is greater than max of cost. So if you notice, what we're saying here is that we have two variables, or two variables. One is about price, one is about, you know, cost or a number. And then we have a relation, which is the greater than sign. And this is very much evaluatable in the sense that you can run this and you'll know if the answer comes back to be true or false, right? To expand a little bit, what we mean by an expression could be either a constant, an attribute, a function over an attribute, or a function over a function of attribute, or a function over two attributes, or so on. Again, I'm not being too precise here. I just wanted to get the general notion across. Operator is whatever, greater than, less than, equal to, within set, or whatever type of relationship. And we need to provide a list of functions. So functions would be like average, max, min, and so on. The full grammar in the paper is a little bit different from what I showed here. I'm just using a subset of what we talk about in the paper just for ease of understanding. I'm omitting a bunch of things here. Now, a quick note or disclaimer about what we're talking about. So I wanted to reiterate that I don't think the specifics of this grammar is the most important thing here. The grammar is meant to be conceptual, and we're going to use it as an illustration of how task might be formalized and operationalized, right? So, just to kind of look at it from the perspective of a logical concept as opposed to a grammar that we will be implementing tomorrow. The other thing is that I need to know, we talk about scientific hypotheses, and I emphasize we're scientific because there's a different type of hypothesis, which are statistical hypotheses. So what makes them different is that specifying a statistical hypothesis requires you to state a null hypothesis, one or more alternative hypotheses, an alpha value, and some interpretation of the results, right? So in that sense, statistical hypotheses are much more complicated, whereas a scientific one where it evaluates to a true false is much simpler and it's much easier to specify. Okay, so here's just some examples of what we can do with this conceptual grammar. So for instance, let's say I have a question about, is the company making money, or the company is making money? I can translate that to something like, well, the total amount of sales is higher than the cost and expenditure. And I can write it out as this statement that I'm not going to read out loud. Going back to the example before, if temperature goes up, volume goes up, then I can reinterpret that as saying there's a positive correlation between temperature and volume. And I'm going to write this hypothesis statement where essentially the correlation between temperature and volume is greater than some constant. And I can talk about this, about other type of distributions. So this is a case where I want to say the horsepower of cars since 2000 follow a normal distribution. And I can write this expression using the Kolmogorov-Smirnov evaluation and with an alpha value of 0.05. And then there's a little bracket thing to filter by year. So this is just some examples. We have other examples where we took this grammar to task in trying to evaluate the 2017 VAST challenge, mini challenge 1, which is the challenge about the nature reserve. So if you want to see kind of the expressivity of this conceptual grammar, you can find it in the paper. Okay, so what, right? I just proposed a conceptual grammar. What can we do with this? Well, I want to suggest that with this grammar, if you believe in what I just said as a foundation, we can now use this grammar to reason about some theoretical concepts about data, task, and viz. So the first thing is, I'm going to introduce this notion about of the hypothesis grammar as hypothesis spaces, right? So consider this simple data set on the right. I have two columns, just cost and price. Now I can write out this, this little simple grammar to essentially describe all the possible hypotheses that we can ask of this data set, right? So, so the only thing I added from what I talked about before is the last row where I specify the attributes being cost and price. So what we're missing is that the user needs to supply, or whoever is writing up this grammar needs to supply a finite list of functions and a finite list of operators. So operators is pretty straightforward. We largely rely on just greater than, less than, or equal to. But the list of functions, you might imagine that there's like an infinite number of possible list of functions, but in reality, that's not really the case. So if you look up a typical SQL database off the shelf, the number of aggregation functions, for instance, is quite limited, actually. So the list of typical functions that comes with these kind of database systems is rather finite. It's not an infinite list of possible functions. Right? So with these two little assumptions, now we can say we have a grammar that describes all the hypotheses that we can ask of this extremely simple data set. Kind of taking it a step further, what we're saying essentially is that given a hypothesis grammar, we can enumerate all possible statements that are parsable by this grammar. Right? So using more of a computer science term, the statements are parsable by this grammar. So with that, we can now say the set of all parsable statements given a grammar spans a hypothesis space. So it's a set, right? And we're going to denote that as H. And we can now measure the size of this hypothesis space, which is, the size is now just the number of possible statements, and we denote it as the vertical bar with H inside. Okay, so this is pretty cool already. Now we have this notion that given a data set with some assumptions, we can now enumerate all possible hypotheses, and I'm using parentheses analysis questions maybe, that a data set can be used to answer. And so we're transforming the notion of the data, a set of data, to now thinking about this in terms of a list of questions or hypotheses. Right? So in other words, any question or any hypothesis that can be asked of any hypothesis that can be asked of the data is already described by this grammar. I think that's pretty cool. So I need to note that with this grammar, we do have some limitations, right? So the first thing is that we're not allowing any sort of feature engineering or data transforms as part of the grammar. So for instance, the grammar doesn't just allow you to add infinite number of columns by, let's say, adding attribute 1 with attribute 2. There's some other minor considerations. So for instance, I didn't talk about filter. I didn't talk about levels of nesting of functions. I'm omitting those kind of minor details, and I think I can do so without the loss of generality. Okay, so let's look at it visually. Now imagine that I have a mathematical space of all possible hypotheses in the universe. So this is like an infinite set, and I'm going to draw that as a big bubble, and that's H. And now, when you're given a data set D, we're going to say the data hypothesis space that we denote as H of D is now a subset of H, which is shown as this. Okay. All right. So it turns out that similar to data hypothesis space, we can now think about using this grammar for other reasons. So we can consider independently the analysis questions that an analyst might have or might want to ask formatted using the same grammar. So it's important to note that when we think about the analyst question, the analyst questions might be completely independent of any data set that they might have, right? So for instance, here's a grammar that I can write that expresses an analyst question about the cost of their company and how it might correlate with the stock prices and the interest rate over the years, right? So the analyst can express these questions independently of any data set. They can just kind of write it out in this form. Okay, so we're going to call this hypothesis space, as described by this grammar, the analyst hypothesis space, and it's denoted as H of A. Oops. Now going back to our little diagram, I now have the big hypothetical H. I have a subspace of H of D. And now I'm adding this analyst hypothesis space, that's H of A. And with these two spaces, we can already start to reason about them in some interesting ways. So for instance, if I have H of D and H of A being completely disjoint, then effectively what we're saying is that the data set that the analyst has cannot be used to answer their questions at all, right? So there's no intersection between the two. I can also think about this as the analyst having a very large hypothesis space, but my data set, the H of D, is significantly smaller. So in this case, essentially what we're saying is the analyst doesn't have enough data to answer all of their questions. And we can think about the inverse of that situation, where I now have a lot of data, and my analysis question is much smaller, so I don't know what that means. That means you have too much data. Not really sure. But it's interesting that to note that when you think about the intersection between these two spaces, because these two spaces are both grammars, which means that the intersection between the two grammars is yet another grammar, right? So you can do the derivation in a pretty straightforward way. Okay, so the last thing, and this is a little bit of hand waving, we're proposing that we can use the same trick to describe all the hypotheses that a visualization can be used to answer. So consider a 3-bar bar chart, a very simple 3-bar bar chart. Now, if you start to think about what are all the questions that I can answer given a 3-bar bar chart, it turns out that there's not that many things you can answer or ask. For instance, I can ask if bar 1 is taller or shorter than bar 2. I can ask if bar 2 is bigger or smaller or equal to bar 3. I can ask if bar 3 is bigger, shorter, smaller than bar 1. And I can maybe ask something about whether the 3 bars form some sort of distribution, some sort of pattern, where my function is just kind of hand-wavingly called fit. And yeah, operators is just the same thing, right? Now, if you kind of think about what I just said here, is that, kind of similar to the endless hypothesis space, this grammar of a 3-bar bar chart is agnostic of data. We haven't touched on data at all. We just kind of talk about the things you can do with a 3-bar bar chart. Right? So there's a minor caveat here, which is that we're assuming that the hypothesis that a visualization can be used to effectively answer will have to be tested empirically before being added to the grammar. So for instance, let's say I give you a 1,000 bar chart that's like spans an entire giant viz wall. Maybe comparing if bar 1,000 is greater than bar 1 is neither practical or possible. I don't know. So if you have very specific context, then the grammar might have to change. Okay, but kind of putting it all together though, so we have our big hypothesis space H, we have H of D, we have H of A, and then of course now we have the hypothesis space of a given visualization, H of V. So in the paper we go into some other relationships between these 3 possible spaces. I'm gonna skip them here, refer to the paper if you're interested. Okay, now, so I propose that at this point, we now have a unified space using the same grammar where we can describe these 3 facets of visualization, namely data, task / hypothesis, and visualization. Right? The nice thing is they live in the same world. They live in the same universe. We describe all of them using the same grammar, so we can start to think about them together. So what can we do with this? So I think that with a formalized and operational grammar of task / hypothesis, there are many possible new directions we can go. I just want to outline a couple of things we've been thinking about, but I will leave the rest up to everybody's imagination. The first thing is going back to my original premise, which is about visualization recommendation. So I mentioned that historically, we think about visualization recommendation as being based on data types, like Show Me and Draco. But now we can consider recommendation of visualization based on this notion of what visualization best helps an analyst answer their analysis questions, right? In other words, we can now think about recommending visualization based on the hypothesis that it can solve. So imagine, for instance, that I have my H of D, and I have a visualization V1, and this is the hypothesis space. And I have a different visualization, so maybe instead of a 3-bar bar chart, this is a 4-pi pie chart, I don't know, right? And it spans a different hypothesis space. And now, instead of thinking about data types, I can now just think, well, maybe I want to recommend HV of 2 or HV2 because the intersection between my data space and my visualization space is bigger, right? But then what if I have something that's like a super powerful visualization called HV3? Should I be recommending HV3 to the user? I don't know, right? So I don't have the answer, but I start to right? I propose that we can start to think about visualization implementation in a slightly different way. Sorry. All right, so the second thing that we can do is to start to think about this notion that we've been calling hypothesis-driven visual analysis. So here's a diagram that I borrowed from people out of the bio side of things. And they think about this cycle of knowledge as an interplay between kind of the human's ideas and what's available in their data. So from idea to data, you go through hypothesis generation, essentially deductive reasoning. And from data to idea, you're doing synthesis, which is a type of induction. So traditionally, I think of visualization as being data first, meaning that the start of a data analysis starts with the bottom, right? So you go from data to synthesis to come up with ideas, and so on. So an analyst would load the data and start performing EDA to come up with new ideas of what they can find in the visualization. But there was a really interesting paper by Emmanuel Zagragan and Kai 2018, where they talk about how this data-first approach can lead to harking, which is hypothesizing after results are known. And they noted that data first is a type of multiple comparison problem, which can lead to spurious findings. If you think about it, the whole notion of a scientific method, which is to say, hey, you have to have a hypothesis first before you can go run an experiment to validate that hypothesis. The whole reason for the scientific method is to try to reduce this type of statistical bias, right? So it's not just me that have been thinking about this. So Kyrie Rita and Jessica Hallman have both really advocated for thinking about visualization as a hypothesis-first approach. What I'm proposing is that now that we have a way to formalize an endless hypothesis, maybe we can start to investigate the effects and potential of this hypothesis-driven visual analysis. So instead of starting at the bottom, we can now start at the top. We have a short paper that we're presenting at a workshop tomorrow where we start to look into this possibility using students with the vast challenge data set. And the last thing is thinking about visualization in terms of evaluation. So we've often claimed that visual analysis tools are supposed to help users in generating, analyzing, and validating hypotheses. But now maybe we can start to really evaluate visualizations along that vein, right? Which is to say, we consider the evaluation of visualization tool in terms of the coverage of H of V in relation to H of D, right? We can now think about how quickly an analyst can trim the uninteresting spaces in the data or in the hypothesis, or sorry, in the data or in their analysis spaces, or how quickly they can identify interesting hypotheses commercially. And finally, how well do the tools actually support the analyst in exploring both data and their analysis or their hypothesis, right? So we've also begun to kind of think about this way of thinking about evaluating visualizations. We had a short paper that's also led by Ashley that got the Best Paper Award at Euroviz this year. It's just a short paper. In the paper, we didn't explicitly mention the notion of hypothesis spaces, but this is kind of a new way that we want to think about evaluation. Okay, so I'm gonna wrap up because I realize I'm the last thing between you and lunch. But the conclusion here is that what we're proposing is kind of a grammar-based perspective to think about data, task, and visualization, and we believe that this can be fruitful. And we propose a conceptual grammar based on this notion of scientific hypothesis and use that as an illustration of how this can be done. And with this grammar, we can now reason about these relationships between data, task, and viz. And we believe that this approach can open doors to possibly exciting new visualization. And with that, thank you very much. Really appreciate your time. If you have questions, here's my email address, and then there's a QR code if you wanted to look at the archive paper. Thank you very much.
Is it okay? Hey Remco, cool talk. I want you to going to ask you to reflect a bit on where some of your thoughts on insights that you've done, as we know from the lovely introduction, happen in this space. Are they vectors that shoot out of this? Are they tangents that fall off of hypotheses as they're coming and going? Are they the same thing?
I have not thought of it. I don't know. I want to say that, right, I talk about the endless hypothesis space as if it's fixed, but I think almost what you're saying is that the endless hypothesis space is mutable, right? It can grow and shrink and change as you actually look through your data. That's the best I got. But like, but we started this work with this, very much with this, with this problem in mind, right? Which is that the thing that Emmanuel came up with about harking was something that we really worried about. It's, so by the way, just for context, in the paper, what they did was they asked a bunch of students at MIT to just explore some data set using some exploratory viz tool. But in this case, the data set they knew the ground truth of. And what happened was the students would do an insight-based evaluation and just tell the researchers what they were finding. And it turned out that something like 65 or 70% of all the insights that the participants reported were all spurious, right? So, the idea that EDA is extremely powerful, but at the same time, it can lead you down the wrong path, I think it's been documented, right? So when we thought about the endless hypothesis space being constant, it's a way for us to say, it's almost like saying you have to pre-register your data analysis and you're not allowed to change halfway through. Right? So this insight thing is really troublesome in that way because it's a mix between EDA and hypothesis testing. Yeah, sorry, that was long-winded, but it was a really good question. Thank you. Yeah, just yell.
Oh, yeah. Okay, it's working now. And very exciting idea. I'm sure this is one of those things Alvita can add to her introduction later on. Another great work. I realized, this whole framework is very early on. So maybe just from the presentation itself, because you want to use very simple examples to explain the grammar, I'm just wondering, is the grammar actually would be able to capture the actual more real world, more complex problems? So if you think of typical vast challenge problems, it's much harder than, say, you can write in one expression. Usually these are kind of also very vaguely defined, find interesting things from the data. So how would you kind of try to address it?
Yeah, so the question I would interpret as saying, what is the expressivity of this grammar, right? So that's a really good question. I think of, sorry, why am I so bad at this? Okay, so we did, well, that's not, I just went through all that trouble, you don't get to see anything. Oh, okay, cool. So we did go through the trouble of trying to use this grammar to see if we can write down the hypotheses that are relevant to the vast challenge. And the short answer is, yeah, it does a pretty good job, right? Now, I will say that this is a very complicated question that we can maybe take offline, but here's the thing. We wanted to propose this conceptual grammar in as simplistic way as possible because when the grammar is simple, it's much easier to reason about it. If I wanted to start adding feature to this grammar, I feel like very quickly we'll approach something that looks like SQL, which is a giant mess, right? So SQL has very high expressivity, but reasoning about SQL is much harder. So this conceptual grammar is meant to be as succinct and as kind of reduced as we can possibly think of it while still being able to do a lot of interesting things. And by no means is this the done deal, right? So for instance, there's no types in here, which is kind of a problem. So there's no data types, there's no notion of types. So in that sense, it's not a complete grammar, it's just really like a way for us to think about things. Cool.
Okay,
you can't not let Min ask a question because he's got a skewer.
I was going to ask a question from Slido first.
Oh,
And then Min, and then we can wrap up. And
Okay,
everyone
cool.
can find Remco throughout the week.
well, go find Ashley because she knows more than I do. But yes.
Can I borrow your mic?
Yeah, go.
So I'm going to paraphrase. This question is from Anna Krisan. So the question is, hypothesis generation and hypothesis exploration. Hypothesis generation and hypothesis confirmation are two different tasks. And how might you balance the trade-offs of the two?
Yeah, these are great questions. So the question is hypothesis generation.
Verification and generation are two separate.
Yeah, they are very different things. So we're actually working on this project where we said, hey, can we actually just visualize a hypothesis space, right? And then the question is, if you let the user just explore the hypothesis space, is that the equivalent of EDA that can lead to, harking and multiple comparison tests? I have no idea. I don't know. And I think this is a really good problem that we're thinking about because maybe people haven't asked about the potential pitfalls of hypothesis exploration because there was no real mechanism to do that before, right? So maybe now with the formalization, this becomes possible, and it's something that we should investigate as a community to say, should we start to think about exploration of hypotheses instead of exploration of data? I'm not sure. And I totally acknowledge that these are, hypothesis testing, hypothesis verification, hypothesis exploration. They're all very different things. Yeah, I don't have a perfect answer right now, but I think that the grammar as a scaffolding to help us think about this is still very possible. Yeah. Min, I'm waiting for your really hard question now.
Hi, Remco, and I think be a nice person first. It's a really good talk, and I certainly looking forward to the first paper, which possibly someone is going to write in the audience to actually do the task analysis based on hypothesis and potential hypothesis. And instead of say R1, R2, R3, R10, and say H1, H2, H10. So that would be wonderful and direction. But now I'm being a little bit sort of negative on that side. So if I were a sort of a machine learning person, algorithmic or machine-oriented person, I would love your grammar. And I would draw a conclusion, say, once you have a hypothesis precisely specified, you can actually test it numerically, and you don't need the visualization anymore.
I totally agree with that, 100%, 1,000% agree, yes. But, so was that the question? Sorry, I interrupted you.
So I was trying to say, what's your view, the role of visualization once you consider the analytical algorithm for hypothesis testing?
Thank you for saying that. That is such a great question. So the challenge is thinking about the data hypothesis space, for instance, right? So let's say I have a data hypothesis space and it's enormously large, right? So even in the simple case of this, just a 2-column data set, the hypothesis space is already quite large. It can be extremely large, right? So here's what we're thinking. We can enumerate all of them, yes, and we can test all of them. We don't need a human to do that. We don't need visualization. We can just literally run all of them. And the problem is each one of them is going to come back with a true false, but now you have 1 billion true falses, and it's like, well, what do I do with that, right? So that's the first part of this. The second part of this is, I actually took it out of the slides. I wrote it in the first time I prepared the slides, but you can start to think about whether the purpose of visualization is really all about reducing the search space or reducing the hypothesis space, right? So I give you a giant, massive data hypothesis space, and the value of a viz tool is to say, these are the things I don't care about, these are the things I don't care about. If you think about this from the Schneiderman's mantra, right, this whole overview first and zoom and filter, right? That's actually very similar to this notion that you start with all the possible things you can consider, and you're narrowing it down to the things that you care about, right? So in that sense, I think visualization has a tremendously important role to play, which is how to help the user reduce the things that they have to consider. And then the last thing I would say is that, yes, individually, every hypothesis statement can be evaluated as true or false. But what's really nice about a visualization, though, is that a single viz can be used to answer more than one question. So this is just a 3-bar bar chart, and this is like a very simple set of functions, right? But think about Tableau. Like, what is the hypothesis space of Tableau? It must be huge. So, right, so I think the value of visualization is somehow this very succinct way to show all the things you can evaluate in a beautiful and simple way, right? And I think in that sense, that is way better than staring at a billion true falses.
Can I add my observation? And so I think something you probably touched upon. So I guess the first thing is we can think about the sort of whether you visualize first, then generate hypothesis, or you have a hypothesis, then you use visualization to evaluate hypothesis. Yeah. So there's 2 processes.
Yeah.
Then particular in a lot of cases, actually people visualize the data, then notice some sort of things unexpected, then they start to have a hypothesis. So that's the one way to think, if you can take that into account, which is consider, as you said, that the space is gigantic.
Yeah.
And the second thing is there are lots of data which we deal with tend to be sparse. And sparse data meant your traditional hypothesis testing will not be statistically significant.
Understood.
So then the visualization allow you to reinforce your hypothesis, or maybe even against your hypothesis, but do a less accurate hypothesis testing. Rather than treat it as a visualization going to offer a definite answer.
Yeah, I agree. I don't have an answer, but maybe we can talk about this offline, because I feel like this is going to go on for 2 hours. But thank you for those questions. Those are very, very good ones. And we have thought about both of those things you mentioned. It's just going to be way too long to try to go into the details. But yeah. All right, well, with that, thank you guys so much.
All right, so we're now at the end of our program. Thank you for allowing us to kick off your Viz Week. Thank you for allowing us to work out all the kinks for the rest of the week. Thank you for our 2 amazing keynote speakers who, I think it was great for us to challenge things that we believe in Viz, and also look toward the future with what John Daniel said in terms of making sure that Viz is going to be relevant in the future. Thank you for all our speakers. Thank you again. Enjoy your lunch, and let's give a final round of applause for everyone.